Awesome.
Okay, it's 8:30, so let's go ahead and get started today. All right, good morning, everybody. How's everybody doing on this chilly morning? Doing good, I hope. It's our last lecture before the Thanksgiving, so I don't plan on having any lectures next week because we're not supposed to, and it's Thanksgiving. I'm probably not going to have my normal office hours because one of them lands on actual Thanksgiving. But I'll be available all of next week. So if you want to, discuss something about the class or need anything cleared up, just shoot me an email or shoot me a message on Discord, and I'd be happy to set up a Zoom. But other than that, I don't plan on opening up my normal office hours. So if you want to meet up, just shoot me an email and then we can set something up there. But besides that, there should be no lectures. Next week should just be a break. So I'm having homework due this Sunday so that you guys don't have. I'm not going to assign anything until after Thanksgiving too. So then hopefully at least for this class you guys can have a break for that. Okay. So the plan for today is we're going to finish up our lecture notes on pipe flow. So last time we went over major losses, and so today we're going to learn about minor losses, and then we'll do some more examples with pipe flow problems. Because depending on the type of problem that it is, or what you need to solve for, the method is a little bit different. I mean, the equations are all the same, but I think it's there's some interesting things that can happen depending on what information you're given and what you're solving for. Okay. Okay, so are there any questions I can answer before we get started today? Okay. Okay, and so last time I think where we left off was this concept of minor losses. Because when we're doing pipe flow problems, you remember the quantity that we're kind of most interested in is quantifying this thing called head losses. And these, we gave this the symbol H sub L, right? And remember, this is something that we plugged into our extended Bernoulli equation in order to quantify, how much energy is lost in the system. Okay. Because whenever you have water or any fluid that's flowing through a pipe, as the fluid, goes throughout the pipe, there's going to be some energy losses. Okay. And the reason for the energy losses mostly are chalked up due to viscosity, right? Because remember, viscosity is almost kind of like the friction of fluid mechanics. So, a pipe is a very kind of constrained system. So as the fluid goes through the pipe, you can almost think of it as like the fluid is kind of rubbing against the sides of the pipe. And just like, when you rub your hands together and friction makes, some of the energy convert to heat, the exact same thing happens for fluids. So as fluids, slide across the pipe, it rubs against it and it loses some energy due to viscosity, okay? And so that's what we mostly went over last time, which was major losses, okay? And so today we're going to talk about minor losses, which is the energy loss that occurs in pipes as the fluid goes through several components. And so remember, the naming convention for these losses is pretty terrible. So, a lot of times, even though it's called minor losses, you might have minor losses that are really, really big in value, okay? So I put other in quotation marks here because it really is just, and everything except for a straight section of pipe, there's going to be some energy loss associated with it, and then we call those things minor losses. Okay, and so the formula for minor losses is very simple. So all you have to do is just to look up this value, which is going to be KL, and then you multiply that by the velocity squared all over 2 times g. Okay, and so the key quantity here is this K sub L. And so this K sub L here is called the loss coefficient. Okay. And so this loss coefficient is you can almost think of it as like a measure of how much energy is lost in a certain component. Okay. And so these loss coefficients are basically assigned per type of component. Okay. Okay. And so some of the components that we talked about before are like an L bend, right? And so an L bend has its own KL. Right? Another component that we talked about was like a valve, right? And so a valve has its own KL. Right? And so the way that you determine these loss coefficients is that you look at your piping system and you see what type of components that you have in there, and then you look up the KL value from a table. Okay. And so there's a table for it in the book. There's actually several of them. But the main one I think you'll probably use is table 8.2. And so 8.2 I think has the biggest collection of loss coefficients for certain pipe components. And so I'm not going to go over that specifically, but I will go over something that's not in the table that is pretty common. So I don't like this part of the book, this next part that we're about to go over, because it takes them like literally 9 figures to explain something that's fairly simple. So I'm gonna attempt to kind of condense it here, but for everything else that's not that we're about to go over, everything else you can find in table 8.2 in the book. So that would be a good one to reference from here on out. I think you can also Google it too. So I think I remember I tried Googling it last year, and I just searched up loss coefficients for pipe flow, and I think the first image that comes up is actually table 8.2 from the book. So it's used quite often for these kinds of problems. Okay, are there any questions on this before we move on? Okay. All right, so let's go over some a loss coefficient concept that I don't think is in the table. Okay, and so the table will cover most of those things like bends and valves and stuff like that. But what's not covered in the table is when the pipe flow goes through either a sudden contraction or a sudden expansion. Okay. Okay. And so when I say a sudden contraction, what I mean is that the flow goes from an area of or a pipe with a large area, and then all of a sudden it contracts into a smaller area. Okay. And so the pipe flow or the flow of fluid goes like this. Okay. Okay. And so on the left-hand side, let's say that the cross-sectional area is A1. Okay. And then on the right-hand side, we have a cross-sectional area of A2. Okay. And so this happens quite often in pipe flow. And kind of the most common place is when the flow enters a small pipe from a large reservoir. Okay. Okay. And so you'll see pipe flow problems where I'll have like a large tank of fluid, and then there's be a small pipe. And so as the fluid goes from the large tank into the small pipe, you need to account for some of the minor losses that occur from this. Okay. Okay. And so what's unique about the situation is that the loss coefficient that's computed actually depends on the ratio between A2 and A1. Okay. And so the loss coefficient is given by a graph that's like this. Okay. And so on the left-hand side, we have the loss coefficient. And on the x-axis, we have the ratio of A2 over A1, okay? And the bounds for this graph is that on the left here, we have 0.0. And the right here, we have a bound of 1.0, okay? And so typically what happens is that as the pipe, the ratio of the areas gets, bigger, then your loss coefficient actually goes down, okay? So the graph actually looks something like this. Okay. And so up here is 0.5, okay? And then down here is 0, okay? Okay. And so how do we read this graph? So let's look at the case when A2 over A1 is equal to 1, right? Right. And so when A2 over A1 is equal to 1, what this means is that the outlet area is the same as the inlet area, okay? Okay. And in this situation, when the outlet and inlet areas are the same, then we don't actually have a contraction. We just have a straight section of pipe, right? And so in those cases, when we just have a straight section of pipe, then we don't have any minor losses that are associated with that. So that's why the graph goes down to 0, as we get down to this end right here, okay? Okay. And so the other extremes of this graph is on the left-hand side when A2 over A1 is 0, okay? And so what this basically says is that A2 is just so small that when you compute the ratio in between them, it's very close to 0. So you can never get exactly 0, but you can get something that's really, really close. Okay. And so in those situations, when you have a very, very, very small pipe with a very, very large inlet, then the loss coefficient that you get from this is just 0.5. Okay. And actually, this is the case that we'll actually use most often. Okay. And so whenever you see a contraction in a pipe go problem, most of the time that you can assume that the ratios the ratio is so small that you can assume a loss coefficient of 0.5. Okay, because otherwise it's a little bit difficult to read this graph because it's you have to kind of draw the lines out here, and when you do that, it's a little bit not precise, because even the figure in the book is not that precise. It's hard to kind of read off intermediate values. So the most common case for a contraction, at least that what we'll see in this class, is for a loss coefficient of 0.5. Okay, but I draw this figure for you mostly just to tell you that this loss coefficient depends on that ratio. So in reality, I think there's probably other software that you can use. I think Chris actually found a really nice MATLAB code he said to compute your friction factors for the Moody chart. And so in reality, there's probably software like that can help you determine what this loss coefficient would be for like an intermediate area ratio somewhere in the middle here. But for this class, most of the time we're going to be working with 0.5 whenever you have a sudden contraction. Okay. Yeah, so the so 0.5, that will be your max KL value for a contraction, and that's the one we're going to use 99% of the time for this class. Yeah. Yep. So the question is, what was that app again? So Chris found a MATLAB code that can, I think you input like the Reynolds number and the surface roughness, and it gives you the friction factor.
Yeah, I can upload it onto the Discord for those of you interested.
Yeah, that would be great. Yeah. Mm-hmm. All right. Any questions on this? Okay. All right. So that's a sudden contraction, and now we're going to do the opposite, which is a sudden expansion.
Yeah, I forgot to ask quickly.
Sure.
For that graph, is it supposed to be a straight line, or are we to assume like it's a curve?
There's a little bit of a curve to it, so it's
okay.
It kind of looks like that. So it's
okay.
definitely not a straight line. And so there's kind of like an area at the beginning where it kind of plateaus a little bit, And then it's not until you reach some kind of threshold that it starts to kind of curve downwards, kind of like that. So yeah, it is a curve. I'm not sure. It's not really quite parabolic. I'd say it's more logarithmic than anything. But
Okay.
but I think the way this was determined was from actually experiments. I think someone just ran a ton of experiments and they just fit a curve to it. Yeah. Mhm.
Thank you.
Okay. And so the opposite of a sudden contraction is a sudden expansion. So a sudden expansion looks something like this. Okay. And so again, we have A1 and A2. Okay. And instead of the fluid getting jammed into a small pipe, the fluid is kind of entering an area where the the flow gets bigger like that. Okay. And so again, we can there's a graph that that describes this. Okay. And so on the bottom here, we have a ratio of the areas. And on the left here, on the y-axis here, we have KL. Okay. One thing you have to be careful when reading this graph is that the ratio for an expansion is opposite. Okay. And so for the contraction, we had A2 over A1, right? And so we basically had the smaller area over the bigger area. This one we have A1 over A2 so that we maintain that it's a smaller area over a bigger area. Okay. And that's mostly just so that we can have a graph that goes from 0 to 1. And so down here we have 0.0 for the ratio, and up here we have 1.0 for the ratio. Because if you can imagine you had it the opposite, then your graph would go from 1 to infinity, and that's not as nice a graph to look at. Okay, and so this this graph right here exhibits similar behavior. So it starts at some maximum value when the ratio is close to 0, or it has some maximum value, and then it goes down to 0 once the ratio is 1. Okay. The thing that's different about an expansion is that instead of having a maximum of 0.5, we have instead a maximum of 1.0. Okay. Right. And so what this tells us is that whenever compared to doing a sudden contraction, the fluid will incur some more energy losses going through a sudden expansion. Okay, and actually twice as much, right? Because we compare 0.5 to 1, for the same kind of ratio of area, we get twice as much energy losses. Okay, so that's kind of interesting. So so when you're doing these kinds of problems, you have to be really careful about thinking about, is this going to be a sudden contraction or is this going to be an expansion, and then to make sure to use the proper loss coefficient for that. Okay. And just like for the sudden contraction, even though this graph shows the values for all different areas, 99% of the time, whenever we have a sudden expansion, we're just going to use a value for 1.0. Okay. Okay. But again, I just show you this graph just to let you know that this loss coefficient, it does depend on the areas, right? And as the ratio gets closer and closer to 1, then the loss coefficient isn't as high, just because you're not expanding or contracting into a much smaller or bigger area. Okay. Okay. Any questions on this? Okay. All right, so these are how you find the loss coefficients for sudden expansions and contractions. And remember, for everything else, you're going to look it up in table 8.2. Okay. Okay. All right. So then, now that we've gone over major losses and minor losses, it's time to kind of put these all together and solve pipe flow problems. Okay. And I do want to say that these are for single pipes. Okay. First question. Yeah, so the question in the chat is, can I explain the significance between the 1.0 and the 0.5 again? Yeah, definitely. And so for the sudden contraction, so you're basically going from a large area to a smaller area, the maximum loss coefficient that we got is 0.5. And so we compare that to a sudden expansion, right? For the sudden expansion, our biggest loss coefficient is 1.0. And so what that tells us is that for an expansion, that naturally incurs more energy losses than a sudden contraction. And so if you have kind of, a contraction and expansion, kind of rapidly going at the same time, or right next to each other, you're going to incur much more energy losses or much more head losses from the expansion than the contraction. So I just made a comment that going from a small area to a larger area is a little bit harder for fluids to do. That's why you incur more energy losses from that. Does that make a bit more sense? Great. Okay. Okay, so now, now that we have everything that we need, we can start solving pipe flow problems, okay? And so I'm gonna let you know that there's, we kind of classify these in 3 different types, okay? So in all situations, you're gonna be computing head losses to some degree, but usually head losses are not the end goal for a pipe flow problem. So usually you wanna solve for something else, right? Because most of the time in practice, when you're designing a pipe flow system, you want to find out things like, how much flow do I need to put into this pipe? What size pipe do I need? How much, length of pipe do we need? Okay. And so the 3 types of pipe flow problems that we'll see are given by the following. Okay. And so the first is type 1 problems. Okay. And so in type 1 problems, we're given the flow rate and the pipe geometry. And so in the problem, I'll basically tell you that the the flow rate is this, the diameter is this, the length is this, okay? And so what you need to determine from this are the pressure differences. Most of the time it's going to be pressure differences and or the head losses. Okay, so that's type 1 problem. So type 1 is the reason it's type 1 is because those are relatively easy. So it's type 1 problems. It's you're basically given all the information that you need, and you just gotta plug it into. You first compute the losses, then you plug into Bernoulli, and then you get the pressure differences. So type 1s are fairly straightforward. And I think problem 4A in the homework was actually a type 1. So in problem 4A in the homework, I gave you everything, the flow rate and the pipe geometry, and I asked you to solve for pressure differences. So 4A is a type 1 problem. Okay, and so let's go over type 2. So type 2, type and pipe sound similar. In type 2, I basically give you the pressure difference or the head losses and the pipe geometry. Okay. And so with that information, the last thing that you need to solve for is the flow rate. Okay. Okay. And so that's type 2. And then type 3, we kind of mix this up a little bit more. Okay. And so in type 3, I give you the flow rate and the pressure drop. Okay. And our pressure drop is the same thing as head losses. And then given those things, you're going to be asked to compute the pipe geometry. Okay. And so pipe geometry with things like diameter or length. Okay. And so problem 4B on the homework is actually a type 3, although it's not really a type 3 problem because it was laminar flow. But we'll do an example of a kind of a type 3 problem later. Okay. Okay. And so these are the three types. So normally when we do problems in this class, we don't really classify the problems like this. So this is kind of unique. But the reason we kind of do this is because type 2, and type 3 problems are solved a little bit differently than type 1. And the reason for that is these often require iteration. Okay. And so what do I mean by that? And so iteration, what that means is that you basically you actually don't have enough information in the problem to fully solve for a solution. And so what you're going to have to do is you're going to have to guess a solution and then check it, and then guess and check and guess and check until you get something that's correct. Okay. And the reason you have to do iteration here is because if you're not given the flow rate, or you're not given the diameter or the length, you're actually not able to compute the Reynolds number, okay? At least not explicitly. Okay. And if you can't compute the Reynolds number, then that kind of throws a lot of things off in this case. Okay. And so in the homework problem, I gave you the diameter so you can compute Reynolds. But we'll see a case later on where you either well, I gave you Reynolds and it was a laminar flow. But we'll see later on that you won't be able to compute the Reynolds number because it's something that you need to solve for in the end. So in those cases, you have to solve with iteration, and it becomes a little bit more tricky. Okay. But first, I'm going to do an example of a type 1 problem just so you can see it all. And this one has a lot of minor losses that are associated with it. So it's a good problem. But before we jump into that example, are there any questions on this stuff? Okay. Okay. And so in this example, let's say that we have water. So our fluid is water here. Okay. And our water has a density of 1,000 kilograms per meter cubed. Okay. And our viscosity, our dynamic viscosity, is going to be 8.9 times 10 to the minus 4 Newton seconds per meter squared. Okay. Okay. And so let's say that the diameter for our pipe is going to be 2 centimeters. Okay. And then the type of pipe that we have is copper, which is a type of drawn tubing. Okay. Okay. I'm also going to give you the flow rate. And so the flow rate is going to be 750 centimeters cubed per second. Okay. Oh, question. Yeah, 10 to the minus 4. Mm-hmm. Yeah. Mm-hmm. Okay. And so the pipe itself looks like the following. So I always mess this up. So that's a lot of twists and turns. Okay. So it starts like this, and it goes like this, it goes like this. Yeah. Okay. All right. So there's a lot going on here. So let's. There's there's a lot of twists and turns. So let me kind of separate each of the different components. Okay. And so what I've highlighted in red right there, all of these are going to be pipe bends. Okay. And so all of these pipe bends are going to have minor losses that are associated with them. Okay. And so in addition to the pipe bends, we also have a bunch of straight segments of pipe as well. Okay. So I'm going to label each of the different components that we need. Okay. And so component A is going to be a straight section of pipe at the beginning. Okay. Component B is going to be this this first pipe bend here. Component C will be this small section of pipe right here. Okay. Component D is going to be the second pipe bend. E is going to be this straight section right here. Okay. Okay. F is going to be this next pipe bend right here. G is going to be this straight section of pipe right here. H is going to be this pipe bend. And then I is going to be this final straight section. Okay. And then we can label some of the lengths here. Okay. And so this length from here to here is going to be 4 meters. Okay. This length from here to here is going to be 3 meters. I know it doesn't look like it, but use your imagination. Okay. All right, this length from here to here is going to be 2 meters. This length from here to here is going to be 1 meter. Okay. And then this length from here to here is going to be 10 meters. Okay. Okay. In addition, we have gravity. Okay, so this is going to be a pipe that travels vertically up, and so gravity is going to go down like this. And so in between our inlet here, so we'll call this 0.1, and we'll call the outlet 0.2. And so in between the inlet and the outlet, we have some height difference that we're going to need to account for in our Bernoulli equation. Okay. And so one other piece of information that we're going to need as we look up the loss coefficients is that these elbows here are threaded 90-degree elbows. Right? Right. So there's a lot going on with this figure. So you know, definitely take your time to write it down and kind of get all the lengths and all the components. Okay. And so what we're going to do basically, so you know, first of all, this is a type 1 problem. Okay. Because in type 1 problems, remember, we're given the flow rate, which is given right here. Okay. And we're given all the aspects of the geometry. So we know the pipe diameter. So the pipe diameter is 2 centimeters. And we also know the lengths just from this figure right here. Okay. Okay. And so what we want to do, since this is a type 1 problem, is we want to solve for the pressure difference between the inlet and the outlet. Okay. Because the flow is going to go from the bottom left up to the top right. Okay. And so in order to flow that way, there needs to be some difference in pressure between the inlet and the outlet. And that's what we're going to be solving for. Okay. Okay. Any questions on the problem setup? I know there's kind of a lot going on with this figure, so if you guys need more time to write it down, just let me know. Okay. All right. So let's go ahead and start solving it. Okay. Okay. And so our starting point most of the time for these problems is going to be our extended Bernoulli. Okay. Okay. And so let's write the difference in between all the Bernoulli quantities at the outlet and the inlet. Okay? Right. And so remember, we for these pipe flow problems, we use extended Bernoulli in head form. Okay, so that's going to be P2 divided by gamma, which is specific weight. Okay. Then we have V2 squared divided by 2G. Okay. Then we have Z2, and all this is equal to P1 divided by gamma plus V1 squared divided by 2G plus Z1 plus shaft head. So that's any kind of work that we're inputting. Okay. Minus the head losses. Okay. Okay. And so this is our full extended Bernoulli. Okay. And so let's simplify some of the terms a little bit. Okay. And so first thing that we'll cancel out is HS. Okay. Because remember, HS represents any kind of work that we're inputting or extracting from pumps or turbines. So we have no pumps and no turbines here, so this is going to be 0. Okay. 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 And so let's take a look at let's next take a look at the velocity terms. Okay. Right. And so let's apply a conservation of mass in order to get the relationship between V1 and V2. Okay. And so since we have a steady situation, we know that the flow rate has to be the same between the inlet and the outlet. Okay. And so, you know, when the flow rates are the same, we basically say that A1 times V1 is equal to A2 times V2. Okay. Yep. So there's a question in the chat. So did I say that this Bernoulli form was head form? Yes, that's correct. And so this is the head form of Bernoulli equation. So you divide everything by, I think by gravity and rho. And so you get everything in terms of, in units of length. Yeah. Mm-hmm. Okay. And so this is our conservation of mass expression. And so one other thing that we know from this problem is that the diameter it's constant all throughout. So the diameter doesn't change. Okay. And so when the diameter is constant all throughout, you know, that means that the area at the inlet has to equal the area at the outlet because their diameters are the same and they're both a circle, right? And so in that case, we can say that, you know, A1 is equal to A2, so those terms cancel out. Okay. And then what we're left with is that V1 is equal to V2. Okay. And so the velocity is going to be the same at the inlet as it is at the outlet, just from conservation of mass. Okay. And so if that's the case, then if V1 is equal to V2, then these two terms are just going to cancel out because they have the same magnitude. Okay. Right. And so once we do that, we can then simplify this expression and solve for P1 minus P2. Okay. Right. So that's a good question. So the question in the chat is, what if they don't have equal area? So if they don't have equal area, then you can get a relationship in between, you know, the V1 and V2, and then include that in your Bernoulli equation. And so if they're not equal, then you have this expression here, and you can get, like, say V1 is equal to A2 over A1 times V1, and then you can V2, sorry, and you can plug that back into this expression up here. Yep. Yeah, good question. And if they don't have equal area, then you're probably also going to have an additional minor loss from either an expansion or a contraction, kind of just like what we just finished going over, right? Okay. But in this case, you know, they are equal, so we can cancel them out. And so let's solve this expression for P1 minus P2. Okay. And so P1 minus P2 looks like this. Okay. And so we multiply both sides by gamma, and then we get the following. Okay, so we have gamma times Z2 minus Z1 Okay. And so this is going to be the difference in height plus HL times gamma. Okay. Okay. And so all I did to get this was I took this equation up here and I just isolated just P1 minus P2. Right. Okay. And so now we just basically need to determine everything on the right side of this equation. Okay. And so the first thing that we come across is gamma. So gamma is we know that since we know the density and we know gravity. And so the other thing that we know is Z2 minus Z1. Okay? And Z2 minus Z1 is simply just the height difference between the outlet and the inlet. And we can obtain that just from our figure. Okay. And so from our figure, we can see that as we go from the inlet and the outlet, we climb a vertical distance of 3 meters during segment C. And we also go up a distance of 1 meter in segment G. Okay? And so the total height difference between the outlet and the inlet is going to be 4 meters. Okay. Right. So that term right there is taken care of. And so the only thing that we have left to determine here is going to be HL, which are the head losses. Okay. And the head losses we need to solve for both the major losses and the minor losses. Okay. All right, so we'll do that on the next page. Okay. So before we do that, are there any questions on this? Okay. All right. So let's compute the major losses. Okay. And so for the major losses, remember these are the losses that are incurred from straight segments of pipe. Okay. And so let's look back on our figure and find out which pipe segments are straight. Okay. Okay. And so our straight segments of pipe are basically going to be everything that's not a threaded elbow. So we have segment A, we have segment C, segment E, segment G, and segment I. Okay. And so all these guys all the ones that I've circled here are going to incur major losses. Okay? And so just write that down again. We have segments A, C, E, G, and I. One kind of rule of thumb that you can use for major losses is to say, if this segment of pipe has some kind of length, then it's going to be associated with major losses. Okay. Okay. And so to compute the major losses, we're going to need to use our Moody chart in order to compute the friction factor. So kind of just like what we did at the end of last lecture. Okay. Okay. And so, because remember, our formula for the major losses was given by the following. Okay. And so our major losses was F, which is our friction factor, times the ratio of length divided by diameter, times V squared over 2G. Okay. And so most of these things we can determine just from the problem. The only thing we have to look up is this friction factor. Okay. Okay. And so remember, to get friction factor, we need two things. So we need the Reynolds number, and we need the ratio of the surface roughness to the diameter. Okay. So let's compute the Reynolds number first. Okay. Reynolds number is always kind of a good place to start. So remember, Reynolds number is going to be rho times V times D over mu. Okay. And so we have everything here except for the velocity, but the velocity we can easily solve for from the flow rate. Okay. Because we're given a flow rate of, what was it? The flow rate is 750 centimeters cubed per second. Okay. And so in order to get the velocity, we can take Q, we can divide by the area. Okay. And so we take 750 centimeters cubed per second divided by pi over 4 diameter squared. And what we get is a velocity of 2.39 meters per second. Okay. And so we plug that back in for Reynolds number, and what we get is a Reynolds number of 53,647.7. Okay. Right.
The velocity is 239, 2.39, or 2000?
Yes, 2.39.
Okay.
Yep. Right. And so since this Reynolds number is greater than 4,000, then we know that we're in a turbulent regime. Okay. And so we're going to have to use the Moody chart in order to solve this. Okay. Okay. And so in order to get the Moody chart, we also need this ratio right here. Okay. Because this is the ratio of the surface roughness over the diameter. Okay. And remember, to get the surface roughness, we have to look this up in a table. Okay, and so I believe the table was 8.1, and we need to do this for drawn copper tubing. Okay. Okay. And so we looked that up in the table, and what we get is a surface roughness of 0.00015 centimeters. Okay. I think the table will give it to you in millimeters, but let's convert it to centimeters just because our diameter is in centimeters. And so we compute this ratio, and we get 7.5 times 10 to the minus 4. Okay. And so what we need to do is we need to look this up in the Moody chart for this particular value, but we don't have this one in the Moody chart. But what we do have is a value of 0.0008. Okay. And so with this Reynolds number and with this ratio of epsilon over d, what we get is a friction factor of 0.02. Okay.
Yeah, using the MATLAB code, I got a factor of 0.0232, so that's pretty close already.
Okay. Yeah. Yeah. Nice. It's good. Yeah, so if you want to use the Moody chart or if you want to use a MATLAB code, that's fine. So in the past, I would tell people to use the Moody chart just because, when you take the final exam, normally you don't have the a MATLAB code in front of you. But since we're doing all the exams are take home, feel free to use that chart or the code, or I'm pretty sure there's some online tools as well, because that's what you would use in reality too. You would use some kind of virtual tool. All right, so there's a question in the chat. So where did the V is equal to Q over A came from? So that's just the relationship between velocity and flow rates. Remember, the Q is flow. And so in order to get velocity from the flow rate, you just divide by the cross-sectional area. Yeah. Yep. Okay, and so you plug all these in, and then we get a major loss of 5.83 meters. Okay. And so the key here for the major losses, and the major losses are nice. So even though we have 1, 2, 3, 4, 5 segments, right? This L right here, since we're doing a single pipe, this L right here is the total length. Okay. Okay. And so what I did basically to compute this was I took the lengths of each of those segments, and so I took this 4 meters, I took this 3. I took this 2, 1, and 10, okay? And so I just added all those up and I got the total length of the system, which was 20 meters, okay? And so I plugged 20 in for this L right here. And that's how I got kind of the major losses for the entire system, okay? Right. Any questions on how we got the major losses?
What value did you give your 5.83, or is that just a scribble notation?
This 5.83, this is the total major losses right here. And so when you plug in, 20 meters for the length, you plug in 0.02 for the friction factor. We know the diameter. We just solve for the velocity right here, and then we have gravity. And so you just plug all that in, and then the major losses are 5.83.
Oh, they don't have units then.
It's a units of meters. Oh, that's what you're asking.
Oh yeah. Oh, in meters. Okay.
Yes. Yeah. So remember, everything in head form has a units or dimensions of length. Yeah.
Oh, okay, right.
Mm-hmm. Right. So the question in the chat is, what was new? And so new, I believe, was 8.9 times 10 to the minus 4. Yeah. Newtons per meter squared, something like that. Right. Yeah. So that was given in the problem right here. Yeah.
That's the dynamic viscosity.
Yes. Yes. Mm-hmm. Or I guess seconds per meter squared. Okay. So that's the major losses. So that's the first part of this. And so now we need to compute the minor losses. Okay. And so the minor losses are going to be all the losses that result from, all the threaded elbows. Okay. Okay. And so the first thing that we need to do is we need to look up the loss coefficient for these elbows. Okay. Okay. And so we look this up in table 8.2. And then what we see is that for threaded 90-degree elbows, the loss coefficient is going to be 1.5. Okay. And so we can plug this into our formula for HL minor. Okay. Okay. And so each of our elbows is going to have a minor loss associated with this, where 1.5 is going to go in for right that. Okay. And so from our diagram, we see that we have 4 threaded elbows here. So we have segments B, segments D, segment F, and segment H. Okay. All of these guys will have a minor loss that's associated with this. Okay. And so what we can compute, since the loss coefficient is just kind of a coefficient, we can just simply add up all of these loss coefficients. Or minor losses, I should say. Add up all the minor losses associated with the elbows. Okay. 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 And so this is going to be KL V squared over 2G, and this is for segment B. And this is going to be for segment D. This is going to be for segment F. And this is finally for segment H. Okay. Okay. And so this is going to be for B. This is going to be for D. This is for F. And this is for H. Okay. And so we're simply just going to be adding them all up together. Okay. And so since they all have the same loss coefficient, the velocity is going to be the same for all of them, and gravity is going to be the same. Okay, we have everything that we need to plug in, and we get a head loss, minor loss of 1.75 meters. Okay. And so if we add this together with our major losses, we can get the total head loss for the entire system. Okay. All right. Any questions on how we computed these minor losses? Okay. Oh, question? Oh, question, is that an R for the first term? Where? All the terms should be KL. Oh, it's HL minor right here. And then HL minor is equal to KL. Oh, the exponent is a 2, sorry. Yeah. Yep. Mm-hmm. Actually, yeah, that's a good question. So I actually don't have the current version that probably you guys have, but the Moody chart, you can probably look it up online too. So it's a very common chart. So you probably just search Google Moody chart. You'll probably find one that's a higher resolution than the one that's in the textbook, because the one in the textbook is actually a little bit hard to read as well.
So the minor losses are only picked up through threaded elbows only?
For this problem, they're only the threaded elbows, but it depends on what other types of components that you have in your piping system. So in this one, the only other component was the threaded elbows. Ah, thanks, Stephen. Yeah, so I guess the Moody chart is on page 431. Okay. And so now that we have the major losses and the minor losses, we can sum them up. And so our total head loss is going to be 7.58 meters. Okay. All right. And so now that we know the head losses and we know that we know the height difference, we can finally plug all of these in and solve for P1 minus P2. And so P1 minus P2, remember, is going to be gamma Z2 minus Z1, which we already determined at the beginning, okay, plus gamma times HL. Okay. And we plug all this in and we get a pressure difference of 113.5 kilopascals. Okay. All right. And so that was an example of a type 1 problem. So, you know, I know it seemed like a lot of calculation, but type 1 problems are actually going to be the easiest ones, because it's you have everything that you need to plug in. It's going to be a lot of work because there's a lot of things you need to look up and a lot of things you need to plug in, but at least all the information is given to you up front. Okay? And so next we're going to do an example of a type 3 problem, just so you can get the idea of, you know, what you need to do, you know, if you're not given all of this information. Okay. But before we get to that example, are there any final questions on this example here? Okay. Okay, so let's do another example. Okay. And so this example, let's say that we have air flowing through a pipe. Okay. And so the properties for air are given by the following. So we have a density, and these are in English units. So we have 0.00238 slugs per feet cubed. Remember, slugs is just a unit of mass for English units, so I think it's just pound mass. Okay. And then our density is going to be 3.74 times 10 to the minus 7 pound second per feet squared. Okay. And so we're saying that this air flows through a galvanized iron pipe. Okay. Let's just say it's an iron pipe. Okay. And in this case, the roughness is given to you, and so the roughness is going to be 0.0005 feet. Okay. And so you don't have to look this up in a table, you know, it's given to you. We're also given that the flow rate is going to be 2 feet cubed per second. Okay. We're also given the pressure drop. And so the pressure drop here is going to be 0.5 psi. Okay. And the length of the tube we're given that is going to be 100 feet. Okay. And so given all this information, what we need to solve for is the pipe diameter. Okay. And so in this problem, we're going to assume that we don't have any minor losses. And so we're just going to consider just the major losses. Okay. But what you'll see is that even though this problem looks fairly innocent, when we're not given the diameter, this actually complicates things quite a bit. Okay. And let's also assume that the pipe is horizontal, and so that we don't have any no changes in height. Okay. All right. Any questions on the problem setup? Okay.
Yeah. Unless stated, are we to always assume that it's horizontal?
Yes. And so most of the time, if there's any kind of verticality to it, it'll probably say in the problem, or you can tell from it from the figure too. And so in this problem, since there's no figure given, then you can assume that it's a horizontal pipe. Yeah. Okay. And so just like last time, let's start with our extended Bernoulli. Okay. And so we have P2 over gamma plus V2 squared all over 2G plus Z2 is equal to the same quantities at the inlet. So P1 over gamma plus V1 squared divided by 2G plus Z1 plus HS minus HL. Okay. And so just like before, let's start with canceling out some terms. Okay. And so since we can assume the pipe is horizontal, then we know that there's going to be no height difference. So Z2 is going to be equal to Z1. Okay. We also know that there's going to be no pipe, or there's no pump or turbine. It wasn't stated in the problem, so we can cancel out HS. Okay. And just like we did last time, since the pipe has, we assume that the pipe is going to have a constant diameter throughout, then we know that the inlet velocity is going to be the same as outlet. Okay. And so what we're left with is just a relationship between the pressure drop and the head losses. Yeah. Mm-hmm. Okay. And so if we solve for that, we get P1 minus P2 is equal to gamma times HL. Okay. And in this case, since we don't have any minor losses, this is going to be just the major losses here. Okay. Okay. And so in this problem, we're given this pressure drop. So we know this pressure drop is 0.5 psi. Okay. We know gamma because that's just going to be the density times the gravity. Okay. And so the only thing that we need to solve for is the major losses. Okay. And so remember, the problem asks for diameter. And so right now there's no diameter actually in the problem, but where the diameter comes in is actually through the major losses. Okay. And so let's write out our formula for major losses again. And so our formula for major losses is friction factor times L divided by D. Let me use a capital L here. Okay. Times V squared over 2G. Okay. Right. And so, we basically need to solve for this guy right here. Okay. And so we plug this back in up here. Okay. And then we use the fact that gamma is equal to rho times G. Okay. And so this gravity and this gravity are going to cancel out. And so what we get is P1 minus P2 is equal to F times rho times L over D times V squared over 2. Okay. All right. Okay. And so we actually still have a lot of unknowns here. So we don't know the friction factor. We don't know the diameter because that's what we're solving for. And we don't know the velocity yet either. Okay. And so we need to basically relate all these guys together just so that we can solve for the velocity, or solve for the diameter, sorry. Okay. Okay. So any questions on this so far? Okay. All right, so let's start with the velocity, actually, okay? And so the velocity, we can use the same relationship that we did before. It's going to be Q divided by A, okay? And since we have a circular pipe, we know that A is going to be pi over 4 d squared. And so V is going to be 4 times Q divided by pi d squared, okay? And so we have everything here except for D, okay? And so we plug in all the numbers. And we get that the velocity is going to be equal to 2.55 over d squared. Okay. Right? And so we can't solve for the velocity outright because we don't know what the diameter is. Okay. And so we can plug this back in up here. Okay. And so that will eliminate v. And so put that in terms of d. Okay. The other thing that we can do, just to kind of make our life simpler, is to convert the pressure into pounds per feet square. Okay. Because all the other quantities in the problem are given in feet, and so it would help us to convert the psi into pound per feet squared. Okay, and so there's going to be 0.5 pound per inches squared. Okay. Okay. And so in order to convert this, we're going to multiply by 144 inches square over feet square. And so this gives us 72 pounds per feet square. Okay. And so we can plug that into our pressure drop above. Okay. Okay. And so what I'm going to do on the next page, I'm going to plug in for the density and I'll plug in for the length because we know all those things too. And then we'll get an expression that has just the friction factor and the diameter. Okay. Okay. Any questions on this so far? Yeah. The arrow from D to D. You mean this this arrow right here? Yeah. So basically, I solve for V. So the V is going to be 2.55 d squared. And what I mean by that is I'm plugging in this whole expression here in for V up here. Yeah, so I'm basically eliminating V. Yeah, I'm eliminating V from the equation. Mm-hmm. Yep. Okay, and so you plug all those in, and what you get is 72 pounds per feet squared is equal to 0.7738 F divided by D to the 5th power, okay? Okay. And so if we solve this equation for D, what we get is D is equal to 0.404 F raised to the 1/5 power. Okay. Right. And so at this point we have a problem because we have one equation here and two unknowns. So we don't know the diameter because that's what we're solving for, and we also don't know the friction factor too. Okay. And so we're kind of at a crossroads. Right? So normally at this point, the way that we solve for F is we look this up in the Moody chart. Okay. But we kind of have a problem because we can't do that, okay? And so let me kind of illustrate why, right? Because remember, to compute F, we need both the Reynolds number and this ratio of epsilon over D, okay? Okay. And so the Reynolds number, remember, is rho VD divided by mu, okay? But the problem is we don't know D, okay? And so if you actually plug in the things that we do know, this can be 1.62 times 10 to the 4th all over D, okay? And the same thing over here, okay? Okay, and so we plug in our roughness from the beginning of the problem, which was 0.0005, and then we divide it by D, okay? And so we can't actually compute these because we don't know D, right? And so we're literally stuck. So we can't really move forward here, at least not explicitly, okay? But what we can do is we can do kind of guess and check. Okay. And so what I mean by guess and check is that we can we're basically going to guess a value for F. Plug that in, solve for a diameter, and then check our results with the Moody chart. Okay. All right. And so we're basically going to start with kind of a what I call like a reasonable figure for F, and then we're going to plug this in and then check to see if we get the same friction factor. So we're going to basically guess one and then check with the Moody chart to see if we get the same friction factor out. And if they're the same, then it's then we're good. We can finish guessing. But if not, then we got to keep try with a different guess. Okay. And so I'll kind of walk you through that process on the next page. But are there any questions on this before we get going with that? Okay. Okay. And so let's start with the reasonable guess for F. And so let's guess that our F is going to be 0.02. Okay. Okay. And so when you're doing these on your own, and you're guessing something, this is not a bad place to start. So 0.02. Okay. And so let's plug this in and solve for D. Okay. Because remember, we had that expression between D and F. And so from this, we get D is equal to 0.185 feet. Okay. And so now that we know D, let's solve for Reynolds number and epsilon over D. Okay. And so from this D, we get that Reynolds number is equal to 8.76 times 10 to the 4th. Okay. And then our epsilon over D is equal to 0.0027. Okay. And so now that we know Reynolds number and we know epsilon over D, we can look this up on the Moody chart. Okay. And so from the Moody chart, if we look up on these coordinates, what we get is an F of 0.027. Okay. And so if we compare this F to the one that we guessed, we can see that we're quite a bit off. Okay. Okay. All right. And so what we need to do now is we need to do a second guess and then check our answer from that. Okay. And so for our second guess, let's use this value that we just computed here And so let's guess that F is now 0.027, okay? Right. And so if we guess that for F, then we get a D is equal to 0.195 feet, okay? And then from here, we get a Reynolds number equal to 8.27 times 10 to the fourth, and then an epsilon over D of 0.0026. Okay. And then we check this again at the Moody chart. And then we get an F of 0.027. Okay. And so since this Moody chart result matches up with what we guessed before, we know that we're in the right answer now. Okay. And so since these two match up, then the diameter that we get from the problem is 0.195 feet. Okay. Okay, and so this example basically shows you how to do this kind of guess and check in order to get the diameter when you can't compute the friction factor. Okay, and so these are the type of calculations that you need to do for like a type 2 or type 3. Okay? So I know I kind of rushed that through the end, but we're out of time, so I didn't want to keep people for too long if you had something else to do. But if you, I'll stick around for a few more minutes if you guys have questions on this example. But thank you everyone for tuning in today as usual. So remember, this is our last lecture before Thanksgiving, so I'm not going to see you guys until after Thanksgiving. So hope everyone has a great break. Take a break. Definitely take some time for yourself. I know it's a bit difficult to see family this Thanksgiving, but at least take some time to unwind. And so I will see you guys after the break. Hope everyone has a good break.
Likewise to you, Professor. Thanks again.
Yep. Thanks guys.
Dr. Tran.
Yep.
Happy early Thanksgiving.
Thanks. You guys too. Happy Thanksgiving. Yep. All right. So Jenny, your question is, when is the last day of class? That's a good question. So I think after the Thanksgiving break, I think we have 2 more weeks. Yeah, 2 more weeks after Thanksgiving. So our last day of class will be on the 9th, December 9th.
Okay, perfect. Thank you.
Yep. Yeah, minute paper. I guess I've been kind of forgetting about those. Recently. I'll put up a minute paper in the next 5 minutes if you want to fill that out. Yeah.
Professor, can you hear me?
Yep. Yeah. What's up, Danny?
So for the guess and check, I've noticed that you told us to start with the F at 0.02, which is the good start.
Yep.
I know that we're looking for D. How did you know to start at that point and not any other?
Yeah. So the answer to your question is because this is a textbook problem, or it's an example in the book. So that's where they started. But in reality, okay. If you look at your Moody chart, your Fs kind of have a certain range in which they fall. So usually there's something on the order of like 0.01, 0.02, 0.00. So I would start with something kind of around there. I think 0.02 for most cases is a decent starting point for the friction factors. So that's not a bad place to start for this.
Right. Okay. So I've noticed that when we found the next F, we also increased the diameter by a little bit, right?
Yes.
Are those like usually the only 2 factors that we're playing with?
So the diameter we actually solved for with this equation on the previous page. So the reason we're guessing F is so that once we have F, we can plug it into this formula 0.404 times F to the 1/5. And so the reason we don't know F in this problem is because, or the reason we don't know D is because that's what we were solving for in this problem. But if I were to give you like a type 2 problem, you would solve for the thing that's unknown would be the velocity. And so it all depends on kind of what you're solving for in the problem.
All right. Thank you so much.
Yep. Did you guys have any more questions for me? Okay. So happy Thanksgiving, everyone. Have a good break, and I'll see you after the break.